Hello there guys, welcome back to another epic inexorable maths video. In this video we're looking for the first time at something called Feynman's trick, or you could also call it differentiating under the integral sign, differentiating inside of the integral. It's also called Leibniz's trick or Leibniz's rule, that kind of thing. Or Hello there guys, welcome back to another epic inexorable maths video. We're looking at Feynman's trick. It goes under many names: Feynman's trick, Feynman's rule, differentiating under the integral sign, differentiating inside of the integral sign. It has loads and loads of names. Feynman, Richard Feynman, the mathematician slash physicist that this is named after, did not actually invent this. He's quite a modern figure, just the last century. It was actually Leibniz, the kind of co-founder, I guess you could say, of calculus. He was the one that came up with what we're about to do, but it was kind of forgotten about, and it was Richard Feynman who popularized it again, okay? He brought it back into the meta, you could say. Now, it is indeed true that we have got differentiating inside the integral before GTA 6, okay? That is true, because this method that I'm about to explain does involve differentiating inside of the integral in order to finally, ultimately, integrate the function, okay? So let's have a look at how we do it, because it's really random. This is the integral that we're going to do, of course, and I've also written this over here because this is something that we really need to know. If you differentiate a constant to the power of x with respect to x, it's equal to that constant to the power of x times the natural log of the constant, okay? That's when the constant is positive. I'm also going to say for this integral that a is a positive number. I've not written it. A is a positive number, just to be clear. Okay, let's get into it. So stay with me, because this might seem like it is not going to make any sense, but it will make sense before long. So I'm going to rename this function f of a. F of a. I'm treating it as a function of a. Do you agree that however we manage to integrate this, it's going to most likely be a function of a, because all the x's cancel out, because this is a definite integral. So this is only going to depend on a in the end. So this is a function of a. Okay. Now, this is the clever bit. Do you see there is a natural log of x on the denominator? Ooh, that's really gross. We don't like that. We do not like dealing with logarithms inside of integrals the majority of the time. They're really messy and gross. Now, do you see that there's an x to the power of a in the numerator? If we hypothetically differentiated this thing with respect to a, because x is a constant, we're treating it as a constant, what we get is, I'm just going to write this down, the derivative with respect to a of x to the power of a would therefore be x to the power of a times the natural log of x, because we're treating x as a constant, okay? So if we differentiate this thing with respect to a, we might be able to cancel out the natural log. And that's really the majority of the time how you do Feynman's trick. You're trying to cancel stuff out by making up some random letter like a and differentiating with respect to it. So let's do it. We're going to differentiate this thing with respect to a. Now, how on earth do we do that? Well, it turns out, I'm not going to give you the full explanation because it's extremely complicated how this works and when this works, but the vast majority of the time, if you want to differentiate an integral with respect to some other variable, all you do is you take the partial derivative of the inside. And I'm going to rewrite x to the a minus 1 over the natural log of x. I'm just going to write this as two fractions here. I'm going to rewrite it as x to the a divided by the natural log of x minus 1 over the natural log of x. So I've not differentiated this yet. I'm just writing it like this because it's going to make it a bit easier to differentiate. Because 1 over the natural log of x, there's no a's in it. There's no a's in it. So this is a constant. It's going to differentiate to 0 with respect to a. Okay, so let's keep going. This is the integral from 0 to 1. And again, the natural log of x is a constant, x is a constant, and a is a variable. And we're just going to use this. So the derivative of this term here is going to be x to the a ln x. And this is a constant, so we just continue to divide by this. We get this, and this is 0. This differentiates to 0. So this is the derivative of our function f of a. It's this thing here. Okay, and a bit hand wavy, I know, but we just cancel these out. Okay, just trust me. And we end up getting this, the integral from 0 to 1 of just x to the a dx, okay? Just like that. And now, this is an integral that we can very, very simply evaluate, right? So this is just the integral of x to the a, which becomes x to the a plus 1 divided by a plus 1, just evaluated from 0 to 1. And this becomes 1 to the a plus 1 over a plus 1 minus 0 to the a plus 1 over a plus 1, which is just 1 over a plus 1. So this is the derivative of this function that we're trying to find, okay? I'm trying to find what f of a is without the integral sign there. Now we know what the derivative is without an integral sign. The derivative is just 1 over a plus 1. So what that means is that the derivative of the function is 1 over a plus 1. So what can we do? Well, we can just integrate both sides now with respect to a. So that means that f of a is the integral of 1 over a plus 1. And what is that? It's the natural log of a plus 1. So it's the natural log of a plus 1. And I'm already saying, guys, that a is a positive number, so we don't need the absolute values here. But we do need a plus c. Now the trouble is, how do we find what c is? We need to know what c is, otherwise this is a bunch of rubbish. Luckily, we can find c. Luckily, we can notice that f of 0 is the integral from 0 to 1 of x to the 0 minus 1 over the natural log of x. But x to the 0 is the number 1. So if a is 0, the whole integral is also 0. So f of 0 is 0. Okay? That means, I'll do it over here, f of 0, which is 0, tells us that 0 is equal to the natural log of 0 plus 1 plus c, just like that. Okay? And that lets us find what c is because we have that initial condition. Now we can see that the natural log of 1 is 0, so c is 0. So I'm just going to write this up here. C is 0 in this question. So we can conclude that f of a in its entirety is just the natural log of a plus 1. And that's it. So this is equal to the natural log of a plus 1, just like that. So for example, if we wanted the integral from 0 to 1 of, let's say, just x minus 1 over the natural log of x, that's when a is 1, then that would be equal to the natural log of 1 plus 1 or the natural log of 2. And this works for any positive value of a that you want. Isn't that nice? So I'm going to make a few more videos on Feynman's trick because this might seem like, oh, okay, it kind of makes sense, but you might be thinking, I don't know if I could replicate this. What if there's no a? What if there isn't an a? What if there's several variables? We're going to deal with all of these different situations and we're just going to practice it until you get really, really, really good. It's a method that doesn't work that often, but when it does, it's really, really OP. So yeah, we do indeed have differentiating inside the integral before GTS 6. Thank you guys so much for watching. I highly appreciate it, and I'll see you in the next one. Cheers.